Well, how's it going, everybody? Today is Chapter 2, Science and the Sky. Today we're going to look at solving the mystery of disappearing ozone. As a result of this unit, you should be able to understand that science is a process and always tentative. Science is limited to observation and experimentation, keeping in mind that observation doesn't necessarily mean what we can see readily with our eyes. Two types of scientific studies and their roles in our own understanding of natural phenomenon, how hypotheses are generated and tested, and the history of ozone as an environmental crisis. In order to take a look at this a little bit closer, we're going to explore yet another case study. Just like we did with the Vikings before, now we're going to look at the concept of disappearing ozone. The depletion of stratospheric ozone caused by synthetic chemicals allows dangerous solar radiation to reach the Earth's surface. The scientific process allows us to understand this relationship more fully. In order to study this, let's look at an individual who spent a bit of her life trying to help us understand what this meant. Susan Solomon is a world-class scientist who, along with her colleagues, helped settle a long-standing debate about the causes for the disappearing ozone above the South Pole. This tropical island you see in front of you is Antarctica. Solomon and her team flew to the Antarctic to collect data about the thinning of the ozone in response to a publication by Joe Farman of the British Antarctic Survey. And if you look closely down here at McMurdo Station, you can see all the way up here, in this area right here, some observation towers here, and these are some living spaces and dorms. And this is a place that you could go if you had an interest in studying more about atmospheric science or climate science or anything else. Just keep on studying environmental science, and if you're interested in atmosphere work, you can continue it as well. So let's look at a little bit of a history. In 1957, beginning of data collection, we were using on-ground instruments designed to extend researchers' senses and measure atmospheric conditions. Remember, we can't see necessarily atmospheric conditions with our eyeballs. Molecular air molecules and other things are way too small for us to see with our own eyeballs, nor can we detect varying concentrations of elements in the air through our skin or eyes. So we need to use instruments that were developed by us to help us understand what's happening up there. And when they were doing this down there, they understood and they first found some indications that there were lower than normal ozone levels being collected, and they were used to make some inferences about some possible causes. So they were detecting these lower ozone levels, and then of course the question is, what's doing this, or why is this happening down there? And specifically, why is it happening in Antarctica? Well, the 1970s came about, and with that decade, they discovered that the ozone layer had thinned to about 33% during the Antarctic spring. Data was collected from over 2 sites and over more than a dozen seasons. And this is important in science because we want to make our data as strong as we can. Imagine if we presented these results with just one season of data from one particular location in Antarctica. What would be the first question you might ask? Well, is this really what's happening, or is this just some data you found in this one spot for that particular instance? So we need to make our data a little bit more robust, a little more strong, a little more convincing, should we say. So to get over a dozen seasons, for 12 seasons we've been doing this, and we found from not one site but 2 sites that ozone layers were thinning. And by how much? About 33% from our data collections. This is making our case much more compelling. Also, connected studies to this data showed there were increases in CFCs, which, when released into the atmosphere, will produce atmospheric chlorine. Now, this becomes important when you look at this particular diagram down here that is all about how ultraviolet radiation from the sun may interact with the chlorofluorocarbons in the atmosphere and what type of chemical reaction happens as a result. Now we're going to go into this more, so don't necessarily worry about that at this moment. First thing, though, is one person. I've done this before, and people have asked me. They said, Okay, I understand UVB radiation. I've heard it so many times, and I understand it. I put it on my suntan lotion, especially down here in southern Florida. It's because we want to avoid some skin irritations or things. But what is UVB radiation? What's UVA radiation? Is there anything else? Like, is there something called UVC radiation? And in fact, there is. So what the heck are these? And as I was studying physics growing up, nobody ever explained to me what it actually was. So I thought I would just take a quick moment. This is the sun, taken from our great agency of NASA. And you can see here that it's taken through a filter, and this is actually what the sun looks like through a filter. It's not what you and I see with our eyes. And in fact, as a reminder, please don't ever look up into the sun with your eyes. But you can see up here in this corner right here, right? This is the Earth, and this is to scale size. So approximately this, not even approximately, this is just about the scale size of the Earth to the actual vast diameter of our star in the solar system called the Sun. And in fact, about 109 Earths could fit lined up side by side to fit within the diameter disk of the Sun you might see in the sky. The chemical reactions, or I should say the nuclear reactions occurring in the sun in the process that makes the sun glow and produce the heat, something called nuclear fusion. We can't do nuclear fusion on the Earth. We can do nuclear fission. We can split atoms, but what's happening in the sun is it's combining hydrogen into helium atoms through magnificent pressures and temperatures. Now, that process of nuclear fusion results in the expelling of certain radiation, and that is what's called the solar radiation you may see and feel from the star. And when that radiation takes certain energy levels and certain wavelengths and frequencies, it is then approximated into ultraviolet radiation, which is a certain spectrum from here, right? And this diagram, now this is a drawing, this isn't real. This is that star right here, the sun, and it's producing these wavelengths and frequency of electromagnetic radiation right here through the process of nuclear fusion. And depending on the wavelength that we have here, you're going to notice there's different frequencies of these electromagnetic radiation spectrums. And the one we're concerned with right now is this, the ultraviolet radiation right here. It's just beyond, or I should say shorter than, the blue wavelength of visible light, and therefore our eyeballs cannot see UV radiation. We can't detect that frequency with our eyes. So we need to make different instruments that can detect it, and we have. So if you look here on this diagram now, we can see that here now is the side view that we are looking at of that atmosphere, and then this is where those clouds were. They're in this troposphere near the ground surface. In fact, all clouds happen in this level right here. And as we move up through the atmosphere here, we reach the troposphere, and then we reach the stratosphere, which is a different layer of the atmosphere, which is home to the ozone layer. And that's what we're going to look at a bit today. When you look at something like this down here, oops, I'm trying to keep my laser pointer going. These are concentrations of different atmospheric CFCs, we can call, in the atmosphere, and that can be detected by satellites. So the interference of the ozone depletion in the Antarctic was connected to the increase in the presence of chlorine compounds produced by CFCs. And we're going to see how that works in a moment. Just to give you another perspective, the sunlight is coming in like this. Right? Trying to do it with my laser pointer here. Coming down like this, and here is that band a little bit zoomed in a little more. Yes, this area is space. I wrote you live here, meaning you don't live there, but this is the Earth. This is, of course, taken by NASA. So this is what we're talking about, right in here. That is our only atmosphere protecting us from the hostility of space. Okay? So let's look a little bit at this atmosphere thing, right? We live in the bottom of this ocean of air. Okay, we stand right here. Some of us climb these mountains too. But we stand right here. What you can notice here is that there's actually different types of UV radiation. And this ozone is a key element in the atmosphere. It's one of the atmospheric constituents that makes up air, the air that we breathe, right? So, although we don't breathe a whole lot of it because most of it is a little bit higher in the atmosphere, mainly in the stratosphere, there is some ozone that does reach the surface. And when that ozone mixes with smoke particulates or pollution particulates, we can produce something called smog when it's at the ground level. And this happens as a result of atmospheric inversions and different atmospheric processes occurring and combined with geologic terrain features on the ground, but often known as a bad ozone mixture. And that smog, a very famous smog you notice in places like Los Angeles, where they do have an inversion happening there quite often. Okay. So the ozone then is part of the atmosphere. The first area we're looking at down here in this pop-out is the troposphere. Troposphere is the lowest air part of the atmosphere. It's approximately 7 miles. Now, it is not steadfast 7 miles. This is a fluid or a gas, okay? So it's a little bit of a mixture along here. It's not like you can go up and walk across the troposphere, or in other words, the tropopause, which is the border between these two boundaries right here. Okay, so it's a little bit not, we're simplifying things here, but it is approximately 7 miles up into the air, which means that our highest mountain peak, Mount Everest, it's about 30,000 feet, is lower than the entire extent on the troposphere. Okay, so you'd have to go above that and get into the stratosphere. When you go above the troposphere and into the stratosphere, you're now into this layer of the atmosphere that contains the ozone, and we can detect that using different sensors. From nowadays, we use satellites and things like that. It's less dense than the stratosphere is, and then therefore it does contain this layer of ozone, which is considered to be O3, oxygen, 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 chained together. Okay. The ozone of the stratosphere helps maintain the perfect, quote-unquote, perfect temperature on the planet. And we put perfect in quotes because, well, it's perfect for life as we know it, right? That's what keeps us stable. Essentially, 0 C to 100 C, or you may know it better as 32 degrees Fahrenheit to 212 degrees Fahrenheit, which is freezing and boiling of water. Okay? So this is the stratosphere. Now, when we think back to the sun and is exhausting its solar radiation radially outward from the sun, and the Earth intercepts some of that energy. Some form of the energy is, yes, in ultraviolet radiation. Some of it is, yes, in visible light spectrum. Hence, we can see during the day because the sunlight, the visible light will reflect off things and into our eyes, and we can detect and decipher those light codes into our brains, and we can see. We can't see with our eyes as UV radiation, but it's still there, and we get evidence that it's still there. And in fact, if you're susceptible to getting suntans or sunburns, all you need to do is go out onto the beach for a day unprotected, and next thing you know, you're burnt. And, well, what happened? No one put you in an oven, did they? But you were actually cooking. That UV radiation you can't see with your eyes was certainly being bashed down onto your skin and causing some, perhaps, maladies in the form of a burn. Now, there's 3 forms of ultraviolet radiation. It's really dependent on wavelength. Here you see those wavelengths represented according to these different A, B, and C as composed up of their wavelengths. You can see here 100 to 280 nanometers and so on, where UVA is 315 to 400 nanometers and UVB 280 to 315 nanometers. And a nanometer is basically 10 to the minus 9th meters, or a billionth of a meter. So you're really looking at something that's extremely, extremely small, so small that the human brains can't really comprehend what that distance of size wavelength might be. And so it's incredibly small. The good news is that our atmosphere is somehow pre-programmed to absorb much of the UVB radiation. And this diagram is trying to depict this because you can see here that UVC radiation is the most energetic and therefore would be the most detrimental to our skins and living tissues. But almost none of it reaches the Earth's surface. It gets fully absorbed in the upper atmosphere. UVB does cause damage to human DNA and human tissues, but luckily, if you can see through these different lines representing tenths of percent, well, I should say tens, not tenths, tens of percent, about 10% of it is absorbed through the atmosphere, and specifically in the ozone layer, or I should say 90% is almost absorbed by the atmosphere, but 10% makes it through to the Earth's surface. So if you're standing on the Earth, about 10% of the ozone layers, the UVB radiation from the sun that day is reaching you. And of course, there is some differentials between cloud dispersion, aerosol dispersion, and depending on if you're in nighttime or daytime. And UVA is the least energetic form, and you can see that about 50% of that reaches the Earth's surface, but it's not as damaging. It's essentially less energetic, and so it actually doesn't cause as much damage. Okay. So science is ultimately trying to give us these tools, where just like I like to say, mathematics is a tool to understand science and physics and the natural world. Science is a tool to help us conduct these investigations to help us understand what's happening. So we just went through this idea of UVC, UVB, and UVA radiation as it reaches through the atmosphere and presents different amounts of absorption based on the atmosphere. All right? The dangers associated with UVB, because many of it, or 10% of it about, reaches our surface, and it's fairly energetic, it causes damage to cells and biological molecules like DNA. Therefore, it could have increased risk of cataracts. This is why most of your sunglasses are UVA, UVB, UVA and UVB protected. There's increase in risk in skin damage, right? That's the skin cancer, the bad burns, the enlarging of freckle spots on the skin kind of thing. And of course, there's an increased risk of cancer. Basically, cancer is just the malaise of living DNA cells becoming damaged and replicating as damaged cells. So the question we come back to is, all right, if we're understanding a little bit about this ultraviolet radiation and as it makes its way through, why then are there varying amounts of this stuff being let through the atmosphere as detected by instruments? And what does that say about our overlying atmosphere? And is there something going on? Well, the CFCs, right? This is a chlorofluorocarbon, and these things were first developed in the 1930s as a commercial coolant in refrigerators and air conditioners. They are the things that used to make the stuff blow cold, and that's why they were used. But in the 1970s, they were used in everything from hairspray to fast food containers. Essentially, the fast food containers, they used it as an expellant to kind of form-fit those styrofoam clamshell containers you used to get. And then hairspray, when you push the button and the hair spray would just come out, that expellant used to be CFCs that used to inject the actual spray into your hair. And over time, CFC molecules entered the air. And they were detected by a British scientist named James Lovelock. Actually, he's actually now Sir James Lovelock in the atmosphere over England. He's a very famous scientist. They were considered safe at the time, and so there was no cause for alarm. You know, this is a scientific revolution that came out, and hey, we can have refrigeration and cool air blowing, and isn't this great? All right. So what if there was a way, though, that if we were going to connect CFCs to some sort of atmospheric change, what are we going to do with all the refrigerants and the air conditioners and the propellants for styrofoam clamshells and hairspray and anything else? So what are we going to do about this? We got to find new propellants or something, right? So when they did the work, there was evidence for the well, the question was there evidence for the possibility that CFCs were destroying the ozone? And in 1985, NASA came out and confirmed that ozone is being destroyed even faster than earlier projections. So the correlation was established between the presence of CFCs and ozone depletion, meaning scientists are starting to understand that ozone is being depleted. Then scientists are also understanding that CFCs are becoming more and more prominent in society. Remember Chapter 1, understanding social patterns and implications and progress in technology and lifestyles? And now we're seeing a correlation. But we can't stop there. We can't just say, I think this is causing that because. Well, we can, but in science we have to try to research and understand this and figure it out so we can definitively provide absolute proof that this is causing that. And if we can't, then we have to keep testing it. So when we look at this idea of the scientific method, the cyclical model that happens in science, cyclical meaning cycles, which is a pattern, really tries to help us gain observations and questions about certain things in the world. So what do we want to observe and question about the causes for the thinning of ozone? Well, so we have to say, well, maybe it's CFCs. So we have to turn this into a testable hypothesis that were based on several possibilities. So it is one thing just to kind of come up with this idea and say, hey, you know what? I think it might be these CFC things were blown into the air. Okay, so you have to go back and you consult the literature, right? I know it's a little bland looking model here, but we consult the literature, which is made and written by scientists and people in society. Not just scientists, everybody, doctors and lawyers and politicians and whoever else, and everyone's got their own spin on it. You generate a question. You choose the questions in which you can investigate, given the funds, the timing, the resources that you have to the best of your ability. Then you can consult the literature to see what's been done. And you build upon the literature. You can see this kind of building thing, and you build into that. And that, what you ultimately build, is going to be then consulted back by this society here of people who are then going to challenge this and try to falsify or reject what you've done in your work. Or they'll try to reinforce what you've done. And that's the process. Once you have this hypothesis, you take this hypothesis and you make a testable prediction. You want to design your study and carry out your experiments to try to help you answer your specific questions. And that's it, nothing else, just your questions. Then you analyze your data, draw your conclusions, run your statistical analysis, do your collaborations with colleagues, and then send it back to the literature for people, bring it back to conferences, bring it back for people to peer review, it's called. Okay. So this hypothesis then is, are cloud particles in the polar stratospheric clouds providing surfaces for reactions that would free chlorine molecules from CFCs? In sunlight, the chlorine molecules will then break up into isolated chlorine atoms that destroy ozone. Is this testable or falsifiable? Well, let's see. The hypothesis. Remember the hypothesis. This is what we want to do. We want to see if this is happening. Okay? So we study various aspects of atmospheric phenomena. And we can look at and see there's normal ozone breakdown and formation. Okay? And is there a change to this process? So you can see here you have this normal ozone where you have O3, which is a naturally occurring element, ozone, O3, and then you have O2, which is oxygen in its free-form nature in O2. Oxygen likes to be with itself, so it goes to oxygen. Well, in nature, normally, if you have sunlight, UVB radiation coming in, which we know happens, then it oftentimes will hit into this particle, will hit into an O3, break it, and then it will go free an oxygen molecule, which will then turn it into O2, and then that free oxygen molecule may run into a different O2 molecule and turn it back into ozone. So there's sort of like a natural balance between by the way, they were looking at the over here ultraviolet effects of UV radiation on plants, and then later they were going to do it on animals, which I know some of you are against, and that is a topic of discussion for the course. But evidence amassed that CFCs were contributing to ozone depletion. The alternative hypotheses were tested, but they weren't supported. As the body of supported hypotheses consistent with that of Solomon grew, the CFC theory became the accepted explanation for what was happening. So as we are going through all this, the international community got together to meet the problem head on, because this problem is not just based in the United States, it's a global thing. Remember, not a single nation governs Antarctica, and yet Antarctica is used as a collaborative base of science and exploration by all nations, but all nations of those who are engaged in science discovery down in Antarctica. So, in 1985, experts meet in Vienna to discuss ways to research and resolve the problem. In 1987, the international community came together in Montreal to produce a plan for dealing with ozone depletion, i.e., phase out the dangerous chemicals like CFCs. So what they did is they went in and they showed that CFCs were destroying ozone. Okay. Remember what the scientists found before, that ozone concentrations were depleting and thinning over the Antarctic, about 33%. So we are introducing more CFCs. The ozone levels and concentrations are depleting. The question you should ask is, how come over Antarctica and not over New York City, or why is it over LA or Miami? Great questions to ask. Put it in the discussion forum. We'll go from there. In 2009, though, the Montreal Protocol is ratified by 196 countries around the world, meaning that this is something everyone cares about, right? It affects all of us. It doesn't just affect one city or one people. It affects the entire planet. So if you look at the estimated and projected changes over time for global emissions of ozone-depleting substances, with no protocol from 80 on, you can see this this purpley color line right here, an exponentially upward growing plot after the Montreal Protocol, which introduced some ratifications. Obviously, the amendment in 1990 in London, which ratified it a bit more, made restrictions a little bit even more serious. Then again in Copenhagen in 92, in Beijing in 99, and ultimately the zero emissions. But in 99, they were producing, basically banned CFCs essentially. And not only that, they're starting to reverse the process of CFCs. So what you're seeing here again is that this in 1979 there was first a year of available images showing the area of thinning over Antarctica, and then in 2006 we had the lowest ozone level ever reached, and from the models that we can see here. But if you look down below, there is hope. Some of you wrote about a doomsday prophecy happening here, but there is hope. See here, this is the type of thing where the correlation between levels of CFC and ozone over the Antarctic are at the beginning of recovery. So here we are with the CFCs into the atmosphere. Concentrations have leveled off. As you can see, we instilled that those different protocols in Montreal, London, Beijing, and called for the ceasing of CFCs. That's in the 70s and 80s and 90s, and you can see that it has peaked and is now tapered off and actually arguably going to start to dip down. And correlated with that is ozone concentrations on how it was being depleted. Now this is the line of best fit for this particular data set here, and as it starts to increase, we're actually producing, well, we aren't, but we're actually seeing an increase of ozone into the atmosphere concentrations over Antarctica, correlated with the reduction of CFCs. So there is stuff that can be done in all this, and science does try to accomplish a lot. So what can you do? Again, this comes back to this idea of this case study, thinking about what's happening in this. Well, in this case, the depletion of the ozone layer is a great example of how science documented a problem and its cause, public action, and confronted the problem. All of the environmental changes we face, from rising levels of greenhouse gases to loss of biodiversity, can be addressed using science. That's what you just saw. You saw the case study of the Vikings, and now you're seeing the case study here of CFCs in global atmospheric ozone concentrations. And you can see how scientific information can make far-reaching consequences. And by improving science literacy as a matter of importance for every individual, me and you and everybody else in society. So that's basically what this is really all about. The message we're trying to send you, at least with this case study and the ones that will be following, which you haven't sent yet, is that things can be done, and environmental scientists and environmental people who work on these problems are doing this. And it's important to realize that things can be done, and people are doing things that can be done. So what can you do? What can be done? Individual steps. Think like a scientist, right? Go outside for 10 minutes and observe the world around you. Make observations of what you see and you hear. Close your eyes and smell the air, or smell the grass, or lick a rock. I know it sounds funny, but try it. I've done it. Lick a rock. Chew a stick. I've done them all. Make sure it's not poisonous, though. Just see what it's like around you. Observe and enjoy the environment that you see. What predictions can you make from your observations, and how can you test them? Do you have any questions about anything? You want to stay informed. You're in a course. You're in college right now. Many of you are working. Some of you are parents. Everybody's got their own lives going on. But you can stay informed. With the advent of modern technology and social media, you can get access to information at your fingertips. So watch a science-related article, TV show once a month, or read a blog, or take courses like this and tell your friends to take more courses like this. And if these courses, if you enjoy these courses, take more. You can do group action. You guys are all in college or working or doing whatever. The point is, you're around other people mostly all the time. So develop plans of action. Discuss things with people. Talk about them. Do some personal little influences. Go out to dinner. Talk about some of the things that you can do with your friends and family over holidays and things like that. So you want to just also support science education. This is close to my heart, but any of you who would like to be teachers, or want to be in education, or just want to be in the know, in the sciences, or work in environmental science or marine biology or anything, you want to just support this science. You won't even just be doing yourself a service. You'll be doing the society a service. And then as groups can form and make some sort of rallying efforts on things, you can affect policy and affect policy change. Attend city councils, go to a board meeting, talk to your employers about what they're doing to change, or not even change, but what are they doing to address some of the environmental concerns. Do you have a recycling program at your work? Do you have an energy reduction program at your work? These kind of things. Make knowledgeable decisions about who your elected officials are, and then serve on local civic committees. If there's anything I can have you think about doing, if you are considering going into any of the science fields, is getting involved in local civic committees. That means going to town halls, or looking on different boards or committees or memberships you can be involved with that help all this stuff happen. So as we approach all this and think about, I hope you enjoyed this lecture. I look forward to your engagement in the discussion forums.